All right, we got another article here. This one by NIST. NIST physicists bring unruly molecules to the quantum party. Scientists have made leaps and bounds in bending atoms to their will, making them into everything from ultra-precise clocks to bits of quantum data. Translating these quantum technologies from obedient atoms to unruly molecules could offer greater possibilities. Hmm. Molecules can rotate and vibrate. That makes molecules more sensitive to certain changes in the environment, like temperature. If you're sensitive to something, it can be a curse because you would like to not be sensitive, or it can be a blessing, said Anna Liebfried. You can use that sensitivity to your advantage, but that same sensitivity has made molecules difficult to control. Recently, physicists at the National Institute of Standards and Technology, NIST, achieved new levels of control over molecules. In a study published in Review Letters, they were able to manipulate a calcium hydride molecular ion made up of one atom of hydrogen and one atom of calcium, with one electron removed to make it a charged molecule, with almost perfect success. And this control opens possibilities for quantum technology, chemical research, and exploring new physics. Let's read a little bit more. Molecules can serve as versatile building blocks for quantum technologies, but they are much harder to control than atoms. Using laser-based techniques developed from atomic clocks, NIST physicists employed a helper calcium atom to control a calcium monohydride molecule nearly perfectly. This method could also allow scientists to use a wide range of molecules for specific quantum tasks, explore physics beyond the standard model, and potentially control chemical reactions. Graduate student April Sheffield in the front, and NIST postdoctoral fellow Baruch Margulis witnessed the calcium ion in their experiment FLASH, indicating the orientation of its companion molecule. Using quantum logic spectroscopy, the team demonstrated near perfect control of a calcium monohydride molecule, an important step in developing molecules for quantum technology. Bounds and bending atoms to their will, making them into everything from ultra-precise clocks to bits of quantum data. From obedient atoms to unruly molecules could offer greater properties. Molecules can rotate and vibrate. This makes molecules more sensitive to certain changes of the environment, like temperature. If you're sensitive to something, it can be a curse because you would like not to be sensitive, or it can be a blessing, said NIST physicist Dietrich Liebfried. I was just repeating what the summary was before. You can use that sensitivity to your advantage. But that same sensitivity has made molecules difficult to control. Recently, physicists at the National Institute of Standards and Technology, NIST, achieved new levels of control over molecules. In a study published in Physical Review Letters, they were able to manipulate a calcium monohydride molecular ion made up of one atom of hydrogen and one atom of calcium, with one electron removed. That means oxidized or reduced. No, sorry, reduced. It's a reduction. Wait, no, it's oxidation because you're losing electrons. Gaining electrons would be a reduction. To make it a charged molecule with almost perfect success. And this control opens possibilities for quantum technology, chemical research, and exploring new physics. Quantum peekaboo. Peekaboo. Was it quantum particles popping in and out of existence? Molecules have more freedom of expression than individual atoms do. A single atom might look like a ball. It appears the same no matter how you rotate it, but even a simple molecule can be a lot more complicated. Calcium monohydride looks like a lopsided dumbbell, with two unevenly sized atoms holding onto each other. Each way you turn it, it looks very different. To control a particle, we need to pinpoint it in one specific state. A molecule has a large number of states it can be in because of its rotation and vibration, said Dalton Chaffee, lead author of the paper. This, in essence, is what makes molecules so much harder to control than atoms. April Sheffield and Baruch Margulis work on molecular control at the Ion Storage Lab at NIST Boulder. NIST physicists want to control the rotation or angular momentum of the molecules so they can do useful things with them. But unlike single atoms or ions, molecules are like ornery teenagers. They don't talk to the team's lasers to indicate their orientation. To gain this control, the team used a technique called quantum logic spectroscopy, first developed to increase the precision and accuracy of clocks made of electrically charged aluminum atoms or ions. To communicate with their molecular ion, the researchers used a calcium ion as a helper. They trapped the calcium helper ion and the charged calcium monohydride molecule together, and since they are equally charged, they naturally repel each other. Think of them as if they were pushed apart by a loaded spring between them, it said. The calcium monohydride doesn't interact well with the laser, but the solo calcium ion does. Using lasers, the researchers cooled the calcium ion, slowing its motion. As the calcium slows its momentum, the molecule friend slows too. Cooling the molecule is critical, graduate student April Sheffield pointed out. And in addition to laser cooling, a cold environment allows scientists to hold the molecular state unchanged for 10 times longer than they could at room temperatures. Then the researchers shine a laser on the molecule to change its rotation. They can't tell if the molecule is rotating, but the calcium ion can. When the molecule changes rotation, the helper calcium ion picks up on it and releases a tiny flash of photons. When researchers see, which researchers see as a bright dot, they tell the molecule to change the rotation back, and the calcium ion flashes again. That double flash of the calcium ion signals two quantum leaps, or two jumps between two different states of the molecule. Seeing that the level of quantum control in action is satisfying as a scientist, said NIST postdoctoral fellow Baruch Margulis, that's quantum mechanics. In our lab, we can see with the camera if our ion is in one quantum state or another, which I find super cool, he said. It's captivating to see it with your own eyes. The molecule can remain in its rotational state for around 18 seconds before the surrounding thermal radiation forces of the molecule to change its state, and the ion stops flashing. That's one of the main results of their study, Margulis pointed out. Those 18 seconds are important, Liebfried added, because it gives the researchers thousands of opportunities to measure the molecule's state before it changes. It's sort of a peekaboo game, if you wish, Margulis explained. As soon as thermal radiation drives the molecule to a different state, the flashes of light from the observer ion cease, and we're able to see that almost as it happens within 10 milliseconds or so. One peek at the ion isn't enough. Scientists checked repeatedly if the calcium ion was bright or dark, proving that they had control over the molecule's state, and the result wasn't a fluke. The team achieved 99.8% success rate, meaning that if they made 1,000 attempts to manipulate the molecule, they were successful about 998 times. Nice. Quantum thermometers and tackling other molecules. During the experiment, the molecule gave a significantly more accurate and detailed depiction of the thermal radiation surrounding it than the thermometer inside the vacuum did, Sheffield explained. This means that molecules can be used as microscopic thermometers. A quantum thermometer could be useful for atomic clocks, Liebfried added, which can be plagued by minuscule fluctuations in thermal radiation. Based quantum thermometer. God, I hate allergies, man. So annoying. It just gets in the way. Just shut the nose off. I don't care, man. Just turn it off. Shut this thing down. I'm busy. I'm doing things. I don't remember where I was. Um, Okay, quantum thermometer can be useful for quantum clocks, precise molecular control. Molecule-based quantum thermometer would even allow scientists to measure specific frequencies of thermal radiation. Precise molecular control also opens up the nearly unfathomably large zoo of molecular species for new quantum technologies. Physicists working on quantum computing or sensors have generally been limited to a few kinds of charged atoms or ions, such as calcium and barium, which are in a small portion of the periodic table. If tools used in this experiment are not specific to any species, which means they can be adapted for other molecules, the tools in this experiment are not specific to any species, which means they can be adapted for other molecules. Ultimately, scientists envision being able to have precise molecular control over chemical reactions, potentially opening new avenues for chemical studies, but that is still a long way from reality, the team cautioned. It's not just a one-off, but it's a demonstration of a protocol that can be used for many other molecules, Margulis added. When you think about a periodic table, it has a finite number of elements. Molecules are more diverse. So, although they are hard to control, there is a huge pool of molecules. If you had perfect control, you could select a candidate based on which tech, whether it's quantum sensing, quantum information. That was I feel like they're doing interesting stuff, but for some reason that article is just boring to read. But yeah, they're doing interesting stuff. Like we'll see what we can do with that. All right. Very, very interesting. Let's see how we can apply that technology in the future. I want to see what kind of things come out of that. What are all these new possibilities you speak of? What are all the things we can do with this technology? That's what I want to know. This is just a start. We're going in the right direction though. All right. So article number 2 for the day. 12 minutes this time. All right. Coffee's helping a little bit.